The next chapter, chapter 4, deals with the concept of transfer functions. To introduce that concept, let's look at the general example of a tank in a process. The input is the inlet flow rate W1, and the outlet flow rate W2 is the output. If we make a step change in W1, we may see a variety of responses in W2 depending on the dynamics of the process. The dynamics of the process reflect the physical properties and physical relationships between the different variables. For example, we might have an unstable response which grows unboundedly to infinity, or we might have a stable oscillatory response which slowly dies and reaches a steady state value. We may also have a first order exponential response, which is very simple. It just reaches a steady state value immediately after some time. How W2 of t responds to a change in W1 of t depends, again, entirely on the dynamics of the process. If we are to write the differential equation and we see a nonlinear term, such as the derivative to the power of 2, then we cannot take the Laplace transform because Laplace transforms only deal with linear functions. In a general situation where we have two variables, one input, one output, W1 of t and W2 of t, we have a nonlinear ordinary differential equation describing the relationship between them. We can approximate this ordinary differential equation by linearizing it using methods such as Taylor expansions. From the approximate linear model of the dynamics between W1 and W2, we can write the variables in deviation form. This is to eliminate all initial conditions that may not be equal to 0. The reason we do this is because when we take the derivative and we take the Laplace transform of a derivative, initial conditions come into the terms. And if they are equal to 0, then the Laplace transforms of the derivatives are very simple to manipulate. Finally, we take the Laplace transform and we have a linear transfer function describing the relationship between the deviation forms in Laplace transform of W2 and W1. The transfer function between them is independent of all initial conditions, as stated previously. Let's look at an example that uses the concept of deviation variables and transfer functions. We have a draining tank which has only one inlet volumetric flow rate Q1 and an outlet volumetric flow of Q. We have a valve on the outlet with a resistance of RV. Some experimental constant data is given in this question, but they are not relevant and they will come into play in the next lecture. The flow head equation H equals RV times Q is used to evaluate the quantities Q and H. If we perform a mass balance on the system, we can write the change of the total mass in the system as the product of the density, area, and the change in height. The density and area do not change over time, therefore they are left out as constants. If we rearrange, collect the like terms, and simplify them a bit, we are ready to take the Laplace transform of this resulting equation. Notice that the derivative term contains the initial condition h of 0. Again, if we collect the like terms, we can rewrite the Laplace equation with h of s on one side and the other variables on the other side. The last term is a constant, and the first Laplace fraction that we see is what is called the transfer function between h of s and qi of s. The dynamics between qi and h can be seen in this very intuitive example. If a step change is made to qi of t, regardless of the initial conditions, the response of h of t will be the same. This is what is meant by having the same dynamics of the process. Finally, let's look at the concept of deviation variables. Deviation variables are defined as the process variables themselves normalized in terms of their old steady-state values. By normalized, it is meant that the original value of these variables is subtracted by the old steady-state value of the variables. The deviation variable is denoted with a prime symbol that is almost the same as the symbol used for differentiation. Notice that by definition, the deviation variable evaluated at time 0 is 0, because the steady state value is the same as the value of the variable of interest at time of 0. Using this, we can rewrite the mass balance equation in terms of the deviation variables and eliminate all the terms concerning the initial conditions. We do this by rewriting the original mass balance and then rewriting the steady state form of the mass balance, which all derivatives equal to 0 due to steady state. By combining the steady state and the original variables, we can see that many of the terms collect into the deviation variables themselves. After taking the Laplace transform and collecting the like terms, we rewrite the similar equation relating h of s and qi of s only in deviation form. The transfer function is explicitly seen here, and no initial conditions are expressed as a leftover term to the right side of qi of s. In the next lecture, we will look at how to linearize different nonlinear models to arrive at very succinct and very concise transfer functions, and we will also look at the initial and final value theorems, which were not covered in this lecture due to a shortage of time. Thank you for listening to this lecture, and I'll see you all on Monday. The initial and final value theorem is a very important concept that allows us to evaluate the initial value and final value of any given time domain function y of t by simply evaluating the Laplace domain s times y of s, taking the limit as s goes to infinity and s going to 0 respectively. Some important assumptions to note are that both limits s to infinity s of y of s and s to 0 y s of y of s are both existent and both well defined. The second assumption is that y of t must be continuous within the set of all real numbers. The proof of the first theorem, the initial value theorem, is as follows. We start out with a definition of a derivative taken by the Laplace transform. Then we evaluate the limit as s goes to infinity on both sides of the equation. The last term evaluates to y of 0 because the limit does not apply to a time domain expression. The first term is indeterminate because we are evaluating the product between infinity and 0. Therefore, it must be separated into two different integrals, one going from 0 to 0 plus, which is a value that is infinitesimally larger than 0, and also the second integral going from 0 plus to infinity. In the first integral, e to the negative st evaluates to 1 because t is essentially 0 in the very small interval 0 to 0 plus. In the second interval, e to the negative st evaluates to 0 because s approaches infinity. The first integral simply evaluates to the integral of the derivative of y, which is simply y of t itself. We take the difference between the different values 0 plus and 0. The second integral evaluates to 0 for reasons mentioned previously. Since y of t is continuous, we know that y of 0 is equal to y of 0 plus and it is also equal to y of 0 minus. Finally, we can equate all of them to the limit taken with t going to 0, y of t. Plugging in the appropriate expressions gives us the rest of the proof. The proof for the final value theorem is much simpler and can be found on page 49 of the textbook. For example, let's find the initial and final values of the following Laplace domain function without having to take any inverse Laplace transforms. For the initial value, we simply go through the motions by substituting in the correct terms. Notice that s appears on both the numerator and denominator and can be cancelled out. Since s approaches infinity, all the powers of s render the function 0. In the opposite case, the final value case, we cancel the s's out from the numerator and denominator, and the only surviving term is the 6 in the denominator. So the final value of the function is 1 over 6. Now let's continue on with the transfer functions and how we can use them to determine the responses of different systems in accordance to different inputs. Let's look back on our draining tank example and recall that the transfer function between the height of the tank and the inlet flow rate of the tank in deviation form is a first order transfer function 1 over as plus 1 over the valve resistance. We can show this in block diagram form by labeling the inputs and outputs and the transfer function between them. Let's find the response in the height of the tank with respect to two different types of changes. The first type of change is a step change with magnitude of m in qi of t. This can be realized as putting a valve on the inlet flow rate and opening the valve, for example, from 40% valve opening to 60% valve opening. Obviously, these values are arbitrary and you can use any values you like. The inlet flow rate, when plotted over time, will resemble a step function with a magnitude of m. Writing the deviation form of qi, the inlet flow rate, is quite easy because the expression for qi of t is simply a step function. Therefore, we can quickly take the Laplace transform of the deviation of qi, which is m over s. We substitute this back into the transfer function between h deviation and qi deviation, and we quickly find that we are dealing with a partial fraction. This partial fraction can be simply calculated as two different constants, alpha 1 and alpha 2, with these following values. Substituting the partial fraction back into the expression for h deviation of s, we can then take the inverse Laplace transform of h deviation of s to find h deviation of t, which is the deviation of the height of the tank in time domain. This simply evaluates to a sum of a step function and a decaying exponential function. Recall that the step function has values of 0 for all values of t before 0 and the value of 1 for all values of t above 0. The normal form of h of t is simply summed by the deviation form of h of t and the old steady state value. We can use this to evaluate the initial and final values of h of t in order to create a plot. As we can see, the initial value of h is simply the old steady state value, whereas the final value of h is simply the old steady state value of h plus a constant which is equal to the magnitude of the step change in qi times the valve resistance. The response is simply a first-order exponential decay between the two steady state values. Let's look at a second type of input, which is an impulse with a magnitude of 1 in qi of t. This is represented by qi of t with qi bar, the old steady state of value of qi, everywhere except for t equals 0, where the value of qi is approximated as infinity. Taking the deviation, we find quickly that qi, deviation of t, simply equals the delta function, which represents the impulse function of magnitude 1. With this, we can quickly take the Laplace transform of qi and find that the Laplace transform is simply 1. Substituting this back into the transfer function between h and q, we come up with a first-order fraction for h. The inverse Laplace transform of h deviation of s is simply h deviation in the time domain, and this is simply equal to an exponential function. Again, we evaluate the values of h at time equals 0 and time equals infinity in order to generate our plot. In this case, the old steady state value of h is h bar. At time equals 0, the height of the tank jumps up to a value of h bar plus 1 over a. Then it decays down slowly back to the value of h bar in an exponential fashion. Note that this case is akin to the example where you open the valve suddenly and then you close it, returning it to its original valve position. Finally, let's look at some important properties of transfer functions. In the time remaining in this lecture, we'll look at the first property, which is the gain and time constant form of first-order transfer functions. Any transfer function can be written as the quotient of y deviation of s over u deviation of s, where y is the output and u is the input. It can be written as a quotient of a constant k over a constant tau times s plus 1. K is the steady state gain represented by the difference in the old and new steady states of the output over the old and new steady states of the input. The time constant is simply the time required for the output y of t to reach a value of its old steady state value plus 63.21% of the difference between the new and old steady state values. This is represented in the following plot. Recall that the gain and time constant form of a first-order transfer function can be expressed in terms of the constants k and tau, where k is the steady state gain, which is simply the ratio between the new and old steady states in the outputs and inputs, and tau is the time constant, which means the time required for the output y of t to reach 63.21% of the steady state gap between the new and old steady states. The diagrams here show exactly what these different constants and equations mean. To prove that the steady state gain actually equals the value k, we start out with an arbitrary input, u of t. We make the input equal to a step function, where the magnitude of step is equal to the steady state gap, u new minus u old. We then take the deviation form of these variables and express the deviation variables in the time domain. Notice that the input can be expressed as a step function multiplied by a constant. We can then take the Laplace transform of the deviation of the input u and write it in terms of 1 over s multiplied by the constant. Finally, we apply the final value theorem and find the new value of the steady state in the output y. Notice that when we apply the final value theorem, we go from time to infinity into s going to the limit of 0. And we must multiply the Laplace transform of y by the variable s. We substitute in for y by g of s, the transfer function, times the input, and we evaluate the limit as s goes to 0. The s in the front and the 1 over s in the back of the equation cancel out. And we're simply left with the steady state value of y, the old steady state value, plus k times the steady state gap in the input. The gain, using the definition, is the ratio between the old and new steady states and the output and input. We simply substitute in the appropriate values, and we discover that the gain is k, just as expected. Now, we should prove that the time constant is indeed equal to tau. Let's start out with the same arbitrary step input, where the new steady state value of the input is simply 1 plus the old steady state value. The Laplace transform of this function is 1 over s. Substitute in for y deviation of s and use partial fractions to separate the two Laplace transform fractions into easily invertible ones. When we invert y of s, we realize that the second term, 1 over s plus 1 over tau, is simply an exponential term with the constant 1 over tau. The first term, 1 over s, simply inverts to the step function. We substitute in for y at time t equals tau. The step function at time tau is 1, and the exponential at time equals tau is e to the power of negative 1. 1 minus e to the power of negative 1 is 63.21%. And k, obviously, as we've just proven, is the gain of this transfer function. Therefore, when t equals tau, the value of the function equals 63.21 of the steady state gap between the old and new steady states of the output minus the old steady state of the output. We continue on with our list of properties of transfer functions. Most systems can be described by a linear ordinary differential equation where the derivatives of y are taken to the power of n with some constants a multiplied in front. Similarly, the derivatives of the input u are taken to the power of m with some similar constants b of m all the way down to b of 0. In order for the transfer function to be proper, we must have the power of the y derivatives, which is n, greater than or equal to the power of the derivatives in u, which is m. When we write the transfer function, we have the powers of n on the bottom, the denominator, and the powers of m on the top, the numerator. If this transfer function is proper, then the system is known as a physically realizable system. If the initial conditions are taken and assumed to be 0, then we can simply leave out all the values of y taken at 0 as well as the derivatives taken at time 0. In this step, I'm simply showing how the polynomial is evaluated. The numerator order m must be smaller than or equal to the denominator order n. For example, the first order time function is k over tau s plus 1, and this is a proper or physically realizable transfer function. The second example is a proper transfer function because the orders of the numerator and denominator are equal. But the last transfer function is improper, so it is not physically realizable. An example of a physically unrealizable process is one where the numerator order of the transfer function is greater than the denominator order of the transfer function. In this example, when a step change is introduced in the input, we realize after taking the Laplace transforms, evaluating the terms, and then taking the inverse Laplace transforms, that the output in response to a step input is an impulse. This is shown in the following plots. Notice that this impulse function takes a value of infinity at time equals 0. Therefore, when we analyze this system, we realize that we have injected an input with finite energy into the system, but the system has responded with an output with infinite energy because the output takes on the value of infinity at time 0. This is physically impossible to achieve in practice. Finally, we have the additive and multiplicative property of multiple transfer functions involved in the system. The additive property states that if we have two different inputs organized in a parallel fashion, they can be summed together using their individual transfer functions multiplied by the individual inputs. And this gives us the deviation form of the Laplace transform of the output. Similarly, when we have two transfer functions arranged in series, we simply multiply the two transfer functions together to the input, and this gives us the output. The last part of this lecture talks about the different nonlinear process dynamics that can be approximated as linear. For example, if we have a draining tank with a pipe at the outlet instead of a valve, we can write the equation relating the height of the tank to the outlet flow rate of the tank using Bernoulli's principle, which is simply a conservation of energy equation. This gives us a relationship between the height of the tank in square root form to the outlet flow rate of the tank Q. The different constants in front of the square root term can be lumped together into one single constant, which we call K of Q. If we perform a mass balance on the system, we realize that there is a square root term at the end, which makes this ordinary differential equation a nonlinear one. In the next lecture, we will see how to deal with this nonlinear form of the ordinary differential equation in order to still take Laplace transforms and arrive at the output response of the height of the tank. Let's start out with this lecture by a simple reminder that the transfer function of a system captures the dynamics of the system. The properties of the transfer function do not change with the initial conditions of the system or the inputs of the system. In other words, we can have any sort of input we want, and according to these inputs, we have different outputs. However, the transfer function itself does not change. Now let's look at the proof that shows that the gain of the transfer function equals limit taken as s goes to 0 of the transfer function itself. If we assume a general form of the transfer function with an mth order numerator and an nth order denominator, we must simplify the terms so that the last term in the denominator ends up as 1. For example, in this transfer function, we must divide all the terms by 4 so that the last term in the denominator equals 1. If we take the transfer function in this very special form, where the last term in the numerator equals a constant k, and the last term in the denominator equals a constant 1, we can introduce an arbitrary input where the steady state gap between the new and old steady state values is 1. It simply equals to the step function with a magnitude of 1. Now we must evaluate the new steady state value of the output y. To do this, we use the final value theorem, which takes the value of y as t approaches infinity. We use the deviation variable and its definition to sub in for y of t. This simply equals the old steady state value of y plus the deviation variable. The final value theorem says that as t is taken as a limit going to infinity, we must take the limit as s goes to 0. Notice that because the input equals a step, it equals 1 over s, and this cancels out with s in front of the final value theorem. We simply substitute in as s approaches 0 and realize that the only remaining terms in a fraction are k over 1, which equals k. Note that when you're taking this final value theorem and you're introducing an arbitrary input, you must use an input that has an old and new steady state. In other words, a ramp input will not be an appropriate one because a ramp does not have a new steady state value. It simply goes out to an infinity. However, a decaying sinusoid has a new steady state value. Regardless of the input function that is chosen, we can now evaluate the gain, which is the ratio of the new and old steady state values. As expected, this value equals k, and this completes the proof that you can simply take the limit s going to 0 with the transfer function in order to evaluate the gain k. Now let's look at a typical nonlinear process. We have the example of the draining tank where instead of having a valve at the outlet, we have a pipe. The outlet flow rate Q is related to the height of the tank in a square root fashion. The constants arise from Bernoulli's principle, and we simply lump them together using a value k of q. This simplifies the mathematical processes following this example. Note that AP is the cross-sectional area of the pipe, and A is the cross-sectional area of the tank. When we write the mass balance, we arrive at the square root of h multiplied by the constant k of q, which makes this a nonlinear ordinary differential equation. We cannot take the Laplace transform of square root of h directly. Instead, we can use Taylor approximations to transform the square root of h into a series of functions that we can take the Laplace transforms of. The Taylor series states that the value of a function equals the value of a function taken at a nominal value plus the first, second, all the way up to the nth order derivatives multiplied by the difference in the value of the function itself minus the nominal value. We can ignore all the higher order terms and simply keep the first order term. We normally choose the nominal value as the steady state value. Using this, we can approximate the square root of h using a combination of the nominal values. If we substitute back this approximation into the original mass balance and take the steady state values of each of the functions and variables, we can write the deviation form of the system in terms of the input qi and the height of the tank h multiplied by a constant. Note that all these functions are linear, so we can take the Laplace transforms. After we take the Laplace transforms, we can group together the like terms multiplied by h and arrive at the transfer function between h and qi. Notice that this transfer function comes from the first order Taylor approximation, so it is most accurate when the value of h is taken around its steady state value h bar. If the value of h is not close to the steady state value of h bar, a new approximation must be made at a new steady state, or the entire first order approximation is invalid and you must use another function to approximate for the transfer function. During the final part of this lecture, let's look at the application of the multiplicative property of transfer functions. Here we have two tanks in series where the inlet to the first tank is Qi, height of the first tank is h1, the valve connecting the first tank to the second tank has a resistance R1. The outlet of the first tank is Q1 and we have the similar constants and values for the second tank. We assume that the fluid density rho is constant and that the tank cross-sectional areas are A1 and A2 and that the flows follow the flow head relation, which is the flow itself equals 1 over R times the height of the tank. Doing the mass balance on tank 1 and taking the deviation variables gives us the transfer function between the height of the first tank and the inlet flow rate. Similarly, we can perform a mass balance on the second tank to give us a similar transfer function between the height of the second tank and the outlet flow rate of the first tank. We realize that the outlet of the first tank is related to the height of the first tank through 1 over the valve resistance. Therefore, the transfer function between those two functions is simply 1 over R1. Similarly, the valve resistance in R2 gives us the transfer function between Q2 and H2, which are the outlets and height of the second tank respectively. Notice that when we write transfer functions, the output appears in the numerator and the input appears in the denominator. If we write this whole system in form of a block diagram, we can relate the different variables in terms of transfer functions in between these variables. Using the multiplicative property of transfer functions, we can quickly evaluate the transfer function between the outlet of the system and the inlet of the system by simply multiplying together these 4 different transfer functions. Note that we are ending up with a second order transfer function in terms of S. This is the end of the chapter on transfer functions, which is chapter 4 in the book, and during the next lecture, Dr. Gopaluni will continue on with Chapter 5, which describes the dynamics of the first and second order transfer functions.